Next, we have Professor Mythili Vutukuru from our department. She is an associate professor in our department. Her research work spans computer networking, operating systems, and network systems. She earned her B.Tech from IIT Madras and did her MS and Ph.D. in computer science at MIT, 2006 and 2010 respectively. Today she'll be diving into Linux network stack. She'll be talking about how network packets are received and processed within the operating system before it is delivered to your application. She'll also be giving a lot of examples, so it's a nice. I'm excited for this. I want to understand how different network stacks and latest network stacks work. Over to you, Professor.
Okay, hello, good morning everyone. So in this talk, I'm going to be talking a little bit under the hood of what happens inside the Linux kernel when we send and receive packets, right? So I'd like to thank my students Debojit and Preeti who are here for some of these slides. So how does this talk differ from in general the other stuff that we learn about networking, right? So normally a lot of you who would have taken some networking course would have seen what are called socket programs. For example, you know that most networking applications are, where is this? Are built as client and server applications where the clients and servers have things like sockets that are listening at some IP addresses, port numbers, and you connect these sockets to each other. You can send and receive messages. So if you've taken a networking course before, some of this is familiar to you and you would have heard these terminologies, right? And a lot of web applications today, web servers, clients, email, gaming, all of these things are typically there is some API like sockets, which is a C++ abstraction, or in other programming languages there could be different abstractions, but all of them point to the same thing, that there is some mechanism available into which you can send and receive messages, and a similar entity on the other side will receive these messages, right? So this is how networking applications typically communicate. So if you look at a networking course, you're going to learn a lot about, what happens when this networking data leaves the computer. You have a layer 2 switching, you have IP routing protocols, and, TCP, congestion control. All of that stuff is what you typically learn in a networking course, which is what happens once this data that an application gives leaves the host. But in this talk, what I'm going to try and talk about is what happens inside the end host itself when you send and receive data. So this content is something that falls in this weird boundary between a networking course and an operating systems course, and so sort of kind of gets left behind in most curricula. Whereas for modern system design, a lot of what happens here is very important when you look at real systems being built out there and where do the inefficiencies arise and so on, right? So in this talk, I'm going to try and demystify this part of it. When a networking application writes something or reads something from a socket, and what happens from that point till the point when the packet leaves the machine, at which point I think there's a lot of networking textbooks that talk about switching, routing, and so on, right? So this is where I'll try and focus in this talk. Okay, so we'll start sort of the deep dive, we'll go step by step. So the first thing, of course, in any operating system, so these networking devices, your Ethernet device, your Wi-Fi adapter are all, devices that connect to an operating system on a desktop or a laptop. And all of these devices are managed by device drivers. So device driver is a piece of code that manages an external device on a computer. Right, so for a networking card, also called an NIC or a network interface card, also there are some device drivers. Different devices have different device drivers. And the first step to sending and receiving data from a computer is actually a device driver talking to that hardware device and configuring it. Right, so these are the basic steps that happen. Every device driver talks to the NIC, the network interface card, through a process known as MMIO or memory mapped IO. What this means is that there are some registers or some places, some pieces of information in the device that your device driver accesses and configures them, saying this is how you have to send packets, this is how you have to receive packets, and so on. So that is the first step that happens. And then from now on, so what we are going to do is we are only going to focus on the receive path here. What happens when you receive a packet on your computer, right? The packet has traversed the internet, has been routed, forwarded, TCP, blah, 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 all of that has happened and the packet has reached your computer. What are the steps that happen until it reaches your application? So we are going to focus on the RX path. The transmit path is somewhat similar and simpler. Okay, so first the device driver has configured the network card. They've established communication saying if you receive any packets, this is what you're supposed to do. So the next thing that happens is when the network card, your Ethernet card or a Wi-Fi card receives some data, receives a network packet, the next thing it will do is it will do something called a DMA or a direct memory access. What this means is it will go to some area of your DRAM, your main memory, which is under the control of the operating system. It will go to some location. How does it know what this location is? The device driver in its initial configuration has given it some information, right? It will use that information and it will go to some part of the OS memory and it will directly copy the packet into that OS memory. Right, so this happens automatically without your operating system, anybody else getting involved. So this is called DMA or direct memory access. After which point the NIC raises what is called an interrupt. So any external device, your network card, disk, keyboard, mouse, anything, when it has an event occurs, you've typed a character on a keyboard, when any such thing happens, any external device does what is called raising an interrupt. This basically tells the operating system, hey look, some event has happened, you got to handle it. So this guy puts the packet into the OS memory and raises an interrupt. Right, so this is just basic interrupt handling that if you've taken a course in operating systems, you should know. So interrupts come from external devices and whenever an interrupt comes, there will be usually, your CPU is running some user program that's, scheduled on the CPU. And that guy is continuing to run, and when an interrupt happens, that is when the operating system comes into play. This is called, it's also called a trap. So when this happens, your CPU's context, whatever is the context of this user program is, the state of all the registers, everything that is saved, then the operating system comes into play. Now some external event has happened, right? The program that is running doesn't know how to deal with it. So the operating system comes into play, it runs this interrupt handler, takes care of that event and then goes back to the user process again. So this is what happens for any interrupt. So is the case for interrupts from NICs whenever network packets arrive as well, right? So there's a lot of stuff going on here, right? So this is not an easy process. You have to kind of, pause this program correctly so that it can resume again correctly. You have to switch from user mode to kernel mode. What does this mean? This means you're going into a more privileged mode where the operating system can do some privileged operations. So all of this is sort of like it takes some number of CPU cycles and this is not cheap to do. So handling interrupts are very expensive. So why am I emphasizing this? We'll come to it later. So anyway, this is general interrupt handling. So also the similar case happens for networking devices as well. Whenever a network packet arrives, there is an interrupt. But a few differences, some small differences when it comes to network interrupt handling is that, so normally if it's just handling a keyboard interrupt, you typed a character on a keyboard, there's a keyboard interrupt, there's a little bit of work to be done, you take that keyboard character, you copy it into memory, you're done. But for networking packets, there's a lot of work to be done when you handle an interrupt. You have to do layer 2 processing, layer 3 processing, IP routing, you have to do the checksum, and if you've studied TCP congestion control, there are these large algorithms that have to be run. Oh, is there a loss? Should I increase my congestion window, decrease my congestion? Like there's a lot of thinking to be done, right? So all of that, doing it during this time when, this process has been interrupted and, some other process is running, you've interrupted it, doing all of that during the interrupt handling is very cumbersome. Therefore, for network interrupt handling, what operating systems do is they split this interrupt handling into two parts, which are called the top half and the bottom half. So the bare minimum that you need to do to handle an interrupt, which is just acknowledge, tell the device that, hey, I've listened to you and, I'll take care of this. That is done in the top half. And then this top half basically schedules the second part of the interrupt handler called the bottom half interrupt handler, which does a bulk of all the TCP IP processing, because that takes a lot of time and you don't want to do it when you have interrupted an existing process. So later on, when the CPU is free, when no other process is running, that is when this bottom half interrupt handler gets scheduled, and this bottom half is the one that fully processes the packets. Right, so this is very unique to network interrupt handling, simply because it is a very heavy weight interrupt handling mechanism that is needed. So the other thing that what happens between the top half and bottom half is that the top half disables future interrupts. So once you have interrupted, you don't want the network card to be constantly ringing the doorbell and saying, hey, there's a packet, there's a packet, there's a packet. So the top half disables interrupts temporarily until the bottom half runs, and when the bottom half runs, it will handle all the packets that have come in. And once the bottom half runs, then it re-enables interrupts again. Right? So what happens during the top half is, your NIC has done the DMA, has interrupted whichever process is running. It temporarily takes a pause, runs the top half interrupt handler and goes back. Okay? So at this point, I'd like to also introduce this terminology of the device driver and the NIC share what are called these TX and RX rings. What are these rings? These rings are nothing but pointers to received and transmitted packets. Now the NIC cannot just dump the packet somewhere in memory and go away, right? It has to tell the operating system where the packet is. So what it does is, a pointer to this packet is stored in what is called this ring. Now this ring is a shared piece of memory that both the device driver and the NIC know where it is. So whenever the NIC puts a packet, it updates the pointer in this. The pointer is put in the RX ring, and whenever the OS runs later, it will look at the pointers of these packets from this RX ring and it processes them. Right? So this is, so far we have done with the running of the top half interrupt handler. So the next step is, now whenever this process that was running that did the top half interrupt handling, it gives up the CPU scheduler runs, there's nothing else to do. So at that point, when the CPU is idle, this bottom half interrupt handler gets scheduled. This process is also called K-soft IRQD in Linux, but it is basically a OS process that handles a bulk of the network processing. Right? So this bottom half runs asynchronously later, not when the packet is received, but when the CPU has free time. So this bottom half runs, and then the bottom half once again makes, so there is this received packet, then you have to kind of now parse the packet, understand what is the layer 2 header, layer 3 header, what is the TCP IP headers, what is the information there. So it creates another data structure called the socket buffer or skbuff. This is the name of that data structure in Linux. There is the skbuff that gets created, and this skbuff is basically has all the packet headers along with a pointer to the packet. Right? So all of this happens in the bottom half interrupt processing. And in the bottom half, as part of the bottom half itself, you also do the TCP IP processing. Now check the head, checksums of all the headers, TCP, congestion control, sequence number, is it received correctly or not? Should I, send an acknowledgement, what acknowledgement? All of that happens as part of the bottom half interrupt handling. By this time, note that you have the packet in memory and you have the skbuff that is pointing to the packet, and this skbuff is what gets passed along to all the TCP IP functions, right? By now the packet is off, it has been plucked off the RX ring. The device driver is no longer responsible for it. This packet is now traversing the packet along with a whole bunch of other pointers to headers. The skbuff has pointers to headers as well as pointer to the packet. This is the guy that's going through the network stack at this point. Okay? And finally, after all the processing happens, all the networking processing happens, the packet has to eventually reach a socket. Remember that at the beginning we said sockets are typically the most common API used to send and receive packets. So an application has opened a socket, an application writes into a socket or reads from a socket. Now, when this packet has been received, the socket buffer, after doing all the TCP IP processing, you identify which socket it belongs to. You look at the port number, IP address, everything. You identify the socket that should receive this packet, and you go take this escape buff, tag it along to this socket. This socket also has a point, some place where it stores all the received data for that socket called the socket buffer. So you take this escape buff, tag it along to this socket, right? So far the packet is in the OS memory with all of these escape buff or RX string was storing pointers to this packet, right? So we have one copy of the packet in OS memory. Now when the application reads from this socket, then this data, this network data, the payload, the information, the message that has been received on the socket is copied into user memory, right? The user has some array or something, some character array that it has asked to, has given as part of argument to the read system call. So when you read from a socket, now the OS and the user space, they do not share memory by default, right? So because of security and isolation. So the user space memory, there is some variable in the user space that is some array that is has to store this packet. Now this packet is copied from the kernel memory to the user memory, right? So at this point, when you read from a socket, all of this story has happened, and the packet that has been processed fully by TCP, now that packet is copied into user memory, and now the networking application, if it's an HTTP GET request, the web server can read the request, send a response back, and so on, right? All of that happens at the user space of the application. Okay, I hope this is clear so far. So as you can see, there are a lot of steps, and this is a very high overhead process. There are many inefficiencies when it comes to the Linux network stack. For example, you have frequent interrupts. Whenever a network packet comes, whichever process is running has to stop, has to save context, jump into kernel mode, go back. So interrupt handling imposes a certain overhead, certain inefficiency in the system. Then the next thing you have is you have this frequent context switching between there are regular user processes running, then there is this kernel process, the soft IRQ, the bottom half interrupt handler that is doing all the network processing. So you have to constantly switch between your actual application and this kernel process, which again there is a context switching overhead involved across processes, right? So there is switching overhead between user space kernel mode, there is switching overhead across processes, and finally there is this packet copy overhead, right? The packet is first DMA'd into OS memory, and then the OS does all the processing, and then the packet is copied into user space. So you have multiple copies of the same data lying around. Now when Linux network stack was designed, network cards had much lower throughput, and all of this didn't seem like it was such a big deal, right? But today what you have is you have hundreds of Gbps of networking hardware coming up, and you have the same operating system with the same architecture that was designed decades ago at much lower network speeds, the same guy running, the same network stack running with higher and higher networking speeds, right? So today, this is from a recent paper, if you take 100 Gbps network card and you run this run it on Linux and run a networking application on Linux that is, simply reading packets, you can nowhere match the line rate, right? You're getting hundreds of Gbps of data, even with multiple threads and, multi-threading, parallelization, whatever you do, the throughput that you get, of course, these numbers may vary, and there's a lot of work on how do you make this number go higher. But the bottom line is you cannot just keep doing whatever you are doing before and expect to match the speed of networking hardwares. As 400 Gbps is also, found in data centers today, and you cannot run the same operating system on top of these higher and higher networking speeds and hope to be able to process. So if you have a web server or any other application that needs to process 100 Gbps of data, it cannot run on Linux the way Linux is today, right? It has not been designed for those kind of speeds because there's a lot of overheads that we've just discussed, right? So today people are coming up with newer ideas, and while I cannot go into a lot of depth of those ideas, I'd like to give a high level flavor of what is it that people are looking at. Right, so on the left here you have the generic network stack where for every packet there's an interrupt, you process the packet, you copy the packet to user space and all of this. One alternative to this that the state of the art today is exploring is you're trying to offload some of this packet processing into the kernel itself, right? So this is called in-kernel offload. Now of course, you can always write, you can hack the Linux kernel, change the source code, write kernel modules to process packets inside the kernel, but that is not something that everybody can do. So today people are coming up with techniques that makes it easy to offload some of this packet processing into the kernel itself, so that you handle the packet here itself, at least most of the packets here itself, and don't do this copying into user space. So the application somehow communicates something to the kernel in an efficient manner, and the kernel handles the packet at this level itself, so that you're avoiding all of these packet copies. So that is one way, pushing things into the operating system itself and avoid crossing this kernel user space boundary. The other technique is what is called kernel bypass, where you say forget it. I mean, Linux, this architecture itself makes my head hurt. I'm going to leave all of this aside. I'm going to directly take packets away from the NIC directly into my user space application and bypass the operating system fully. Right? So the next set of optimization techniques are called kernel bypass methods. Right? So we are going to briefly look at what these two are. Of course, there are pros and cons, right? So as you can see, this one is likely to give you better performance because you are kind of getting rid of all of this clunk here and going directly to user space. But at the same time, you are losing control of the operating system. Whatever control the operating system had with respect to, maybe you have existing scripts and tools and all of that don't work over here. They work better over here, right? So there is a trade-off. So first, let's look at what are these in-kernel offload techniques. So the most common and popular one is what is called eBPF, or Extended Berkeley Packet Filter. I mean, let's not worry about how this name came about, but what this means is that today in the Linux kernel, you can actually write some programs called eBPF programs, which actually, where you can write some packet processing, look at the packet, if this is the header, do this, do that. You can write packet processing code in this framework called eBPF, which gets compiled and verified and then loaded into the kernel. So now this is not like hacking the Linux kernel to do packet processing. This is much more safer. You are guaranteed that this eBPF code will not crash the kernel, because there is a verifier step over here that ensures that the code you're writing is safe and it can be, dynamically loaded into the kernel. So you can write these eBPF programs, and then these eBPF programs run at what are called hook points, right? There are specific places inside the kernel during the packet processing where the OS has, given you a place to push this eBPF code, when in the device driver during the TCP/IP processing, when you are, assigning packets to sockets. There are multiple hook points inside the kernel where you can write your own code, eBPF code, to customize the packet processing. So earlier everything had to go to the user space. Now everything does not have to go to the user space. A lot of the stuff you can handle within the kernel itself safely by doing custom packet processing in eBPF, right? And there are things like eBPF maps. So there are ways. So an eBPF map is nothing but a shared, key value store, a hash table kind of data structure where the user space can say, hey, for these kind of packets you do this, and the eBPF program will take instructions from the user space or give back information to the user space, exchange information, and you can actually do custom packet processing inside the kernel, right? So this is one way, and there are several hook points, right? So I'll just talk about a couple of the hook points. One of them is what is called the XDP hook, which happens directly at the device driver. As soon as the device driver starts, you can actually run this XDP hook. So, a lot of simple packet processing you can do here. Then there is something else called the TC hook that runs later on during the TCP/IP processing when you have parsed the TCP/IP headers. So here you have more information available to process the packet. Here you have less information, but this is faster. So there are different trade-offs. There are multiple ways in which you can, multiple hook points where you can run these programs. Now eBPF has many applications today. For example, things like firewalls, you're getting a lot of extra traffic. Instead of this traffic going all the way to your user space program through these 20 different steps we've seen, you can just drop it at the device driver itself. You can look at the packet, you can do some custom packet processing, you can drop the packet. And things like observability, collecting statistics about applications, you can write such code in eBPF, and In fact, people are also offloading, if your application is doing some processing, a lot of the common case processing that can be done quickly can be offloaded into the kernel, into eBPF programs. So today there is a lot of interest in eBPF. It is being developed very actively as part of the Linux kernel, and there are many interesting applications that are being built on eBPF. Right, so maybe I'll take a couple more minutes. I'll quickly go through this kernel bypass method as well. So what this kernel bypass says is it's slightly different from eBPF. In eBPF, we were pushing custom logic into the OS. Here, what we are saying is let's just bypass the operating system, right? So you can write a program in the device driver that will basically take all the packets and directly copy them into the user space application, bypassing all the TCP/IP processing that happens inside the kernel. So there are special type of sockets. So normally you have TCP sockets, UDP sockets. You also have a type of sockets called AF/XDP sockets, which basically whatever packets that match a certain pattern at the XDP hook, which is the device driver hook, you can write an eBPF program that will just directly pass them on into your user space program. And if you have device driver support, you can actually tell the NIC to DMA the packet also into user space. Now there's no more packet copies. You don't have to copy the packet into OS, copy it to the user space application. You're completely bypassing the kernel. You're basically telling the device DMA the packet into the user space application, and whenever the packet comes, just give it to the user space application. You're completely taking the OS out of the loop, right? So this is called AF/XDP. These are a special kind of sockets on which you can build applications. So all of these things, eBPF and XDP, they all work together, right? So when you get a packet at the XDP hook, you can do things like you can drop the packet, or you can forward it through the TCP/IP stack into regular applications, or you can take the packet, give it to this AF/XDP application that has bypassed the entire kernel stack, right? And this XDP and eBPF, they are also used to connect up containers. They work along with virtual devices that are used to connect up containers. So eBPF and XDP together, they actually form a very important part of the cloud networking stack. And this lets you run networking applications efficiently on the cloud at high performance. Right, and finally DPDK is also one more. It's slightly more widely used than AF/XDP, which is somewhat newer. So DPDK, or Data Plane Development Kit, this was initially pioneered by Intel for their networking cards, but now support is widely available for all high-speed networking cards. So what DPDK does is also similar to AF/XDP, where you're completely bypassing the kernel. You put in some kind of a dummy device driver in the kernel that doesn't do much, and then your device driver is actually a user space device driver, which directly talks to the NIC, gets the NIC to DMA packets into user space memory. And now in user space memory, you have a lot more control. For example, DPDK does things like huge pages, which let you, avoid TLB misses and access memory much more efficiently. And it pre-allocates all these packet buffers so that you don't have too many pointer traversals when processing packets. So there are a lot of optimizations that DPDK does, but the basic thing it does is there's a poll mode driver, there is a user space device driver that disables any kernel processing, and periodically it will go to the NIC, get a batch of packets directly into user space and process them, right? So this basically eliminates all the inefficiencies of the Linux kernel stack. Now with all of these techniques today, networking applications can actually very easily get 100 Gbps on a small number of CPUs, with AF/XDP with 6 threads, DPDK using 4 threads, with a small amount of CPU usage, you're actually able to sink in and, process, digest hundreds of Gbps of data very easily, right? Without all of this, it is actually very challenging on the bare bones Linux network stack, but today with these techniques, it is actually possible to build high performance networking applications very easily. So this is the summary of my talk. Just to recap, I've basically told you how the traditional Linux network stack works, from the packet coming in, DMing into the kernel, packet processing, all the context switching, copying it into user space, the inefficiencies involved there, and the 2 optimizations that are used today. So given that you don't want to do this dance across user space, kernel space, crossing these boundaries, there are two ways. Either you push your packet processing into the kernel itself. There are ways to do that safely using eBPF. Or you say you want to bypass the kernel fully, take your packet directly into user space and you deal with it in user space using frameworks like AFXDP or DPDK. And today, the state of the art, if you're building any high performance networking application, so today the buzzword in the industry is what is called NFV or network function virtualization. What this means is I'm going to build whatever was built as software earlier is whatever was built as hardware earlier, a lot of that stuff like firewalls, load balancers and various gateways and routers are actually being built as software today instead of hardware. And this software needs to perform well, and it is using frameworks such as these that we are hoping to see high performance networking applications in software, which is driving the trend for NFV, right? So I think I'm out of time here, so I'll stop. I'll be happy. Do I have time for a couple of questions? Yeah. Okay.
Ma'am, as you said, the packet processing actually performs in the kernel mode, and since kernel mode is a non-preemptive in nature, if any big packet processing program are there, will there be any starvation of other programs?
Yeah, so that is why it happens in a separate process, right? The bottom half, the K-soft IRQD process. So that is not non-preemptible.
Oh.
So which is why the non-preemptible interrupt handler is actually, the top half is actually very slim. And most of the processing happens in the bottom half. And then you could have starvation. For example, at high speed, you may have this K-soft IRQ not getting enough cycles and not processing packets, right? That can also happen.
Okay, thank you.
Hello, thanks for the talk.
Yeah.
I have a question like, especially in data centers, we see the trend that most of the network function is moving into SmartNIC. So even NVIDIA, AMD, Intel, they are coming up with SmartNICs, and almost all of the network functionality has been like handled by them, and they are freeing up the CPU to run user programs.
Yeah.
So how do you see like this evolution going ahead? Like,
Yeah.
will the kernel evolve, or this is a permanency that we will see in the future?
So that's a good question. So there's actually in this set of things, right, there's actually another thing which I didn't talk about. So you're moving it into the kernel or you're doing kernel bypass. The third option is you're actually pushing it into smarter hardware. So you're having programmable hardware, smart NICs with attached FPGAs or programmable switches, all of which are kind of, you know, absorbing some of the packet processing so that everything, your kernel, user space, everything is freed up. So that is also a trend. So I think these are complementary. I don't necessarily see one as overriding the other because this hardware is expensive, right? And you are in some sense locked into a certain hardware. Things like, suppose you want to migrate your VM from one machine to the other. If you're locked into a smart NIC, you are basically limited in your VM migration capabilities. So there are pros and cons to doing things in hardware. It is obviously more efficient, programmable hardware versus doing it in the kernel or kernel bypass. So the way I see it is both of these will go hand in hand, right? And both are valid ways to make your applications perform better. Okay.
Yeah, so with that, we'll end the session.
Okay, thank you all. Any more questions? I'll be happy to talk to you during the tea break. Thank you.
Yeah, I'd like to invite Professor Shivaram to provide a token of appreciation to Professor Mythili.